Hello, welcome to the first video in the physical science topic called radioactivity. This is the introduction. Now, I've most likely sent you around the school to find the most radioactive spot, and if I haven't, I will be, and we'll be talking about that in class. So let's just skip over that. That's just a reminder to me that we should do it. Now, radiation is not the same as radioactivity. Most of you have probably heard the term radioactivity, and you've also heard the term radiation. But in physics, the two are not the same. Radioactivity is part of the broader area called radiation, and radiation includes all forms of transfer of energy, whereas radioactivity is pretty much only specifically related to the transfer of energy due to what's happening inside atoms. And we'll go through a couple of examples to contrast those, just to make sure we're all on the same page. Most likely you've heard the term radioactivity or radiation used in a broader sense on the news or on programs and things, and we just need to make sure we're talking about the same thing. Now, radiation, because it's a very broad term in physics, it includes both what's called ionizing and non-ionizing radiation. And if we remember to the unit we just did, an ion is an atom that has gained or lost electrons. It's no longer neutral. And so some radiation can cause that, whereas other radiation doesn't cause that and is called non-ionizing radiation. Now, in physics, the most common use of the word radiation refers to ionizing radiation, whereas outside of physics, probably the most common use of radiation is actually referring to non-ionizing radiation, so it gets a bit confusing. A couple of examples of non-ionizing radiation. There's heat. The mere fact that you can feel a heater, energy is going from your heater to your hand or your face, and that's a form of radiation because energy is being transferred, but it's not a form of radioactivity, because it doesn't really involve atoms. Radio waves, form of non-ionizing radiation. Microwaves are a form of non-ionizing radiation, so nothing to do with radioactivity. Visible light, the mere fact that we can see things, is radiation, and light is a form of energy transfer, but again, nothing to do with radioactivity. Now, we also just need to recap our understanding of isotopes. Hopefully it's pretty fresh in your minds because we've only just done it, and that is atoms. All atoms of an element have the same number of protons. That's what defines an element to us. However, some atoms can have different numbers of neutrons. Now, because they've still got the same number of protons, they're the same element, but they have different masses because most of the mass is, of course, in the nucleus. And these guys will all be called isotopes of the same element. And I'll show you a diagram or a picture shortly to help clarify that. Now, isotopes have similar chemical properties because they all have, all the isotopes of the same element all have the same electron configuration, and chemistry is pretty much defined by the electrons. They have different physical properties because in terms of atoms they weigh different amounts, and therefore physicists can actually separate them based on their physical properties. Here's an example we looked at in our first unit, and this is magnesium. These are isotopes of magnesium. They're all 12 because they all have 12 protons, but you can see here their mass numbers are different because they vary in the number of neutrons: 12 neutrons, 13 neutrons, and 14 neutrons. And we would call that, and in this section we pretty much identify most of our isotopes just by their name and their mass. Magnesium 24, magnesium 26, and of course this would be magnesium 25. We also had carbon, carbon 12, and carbon 14. How many electrons should be orbiting around it? Hopefully we all recognize there should be, if it's neutral, 6 electrons. Now, in physical science, in radioactivity, we're only going to be looking at particle radiation, and that's where we have an energy transfer, and that's occurring because of moving subatomic particles. Now, three types of radiation we're going to look at. First one is alpha radiation, and that's where this moving subatomic particle is actually the nucleus of a helium atom. And if I asked you to picture what a helium atom looks like, hopefully you'd say, well, it's element 2 in the periodic table. Typically it has a mass of 4, so the nucleus is 2 protons, 2 neutrons, and it has 2 electrons orbiting around it. Now we're talking only about the nucleus, and so alpha radiation is the nucleus, no electrons. So we're just expelling the nuclei of a helium form. Beta radiation, that's when the particle that we're talking about here are energetic electrons. And we should also know about positrons, because beta radiation also emits positrons. Positrons are the antimatter equivalent of electrons. However, the positron beta decays outside of our physical science course, but we'll mention it briefly like then. And the third type of radiation is called gamma radiation, and that's when we're emitting things called photons from within nucleuses. Three types of radiation: alpha, beta, gamma, named after the Greek alphabet. And we'll look at those in a lot more detail in coming up videos. Now we should also quickly go through a broad definition of radioactivity. And this is probably the best one I've managed to find, and you can probably find some others out there on the web if you want to, or in textbooks, but this one's alright. And it says radioactivity can be defined as the spontaneous and uncontrollable decay of an atomic nucleus resulting in the emission of particles and rays. Let's just quickly go through it, make sure we understand what it means. So spontaneous happens instantaneously. There's no warning, it just happens. And so if you have a whole lot of atoms, and you know that that atom or that element is radioactive, if you're looking at all those atoms, you can't pick which ones are going to decay. There's no warning signs, but some of them are going to decay. It happens, bang, like that. Uncontrollable. So even if you get a hint that one of those nucleuses is going to decay, you can't stop it. Like you might have something where an atom which has a very short half-life, and we'll do half-lives in another video coming up, and what that means is there's a very high probability that a nucleus will decay fairly quickly. So you might have 100 of those nucleuses, and you know they're all going to decay within about 5 minutes, but you can't stop them. There's nothing you can do about it to stop them. It's out of our control. It's happening on the atomic scale. Now, resulting in the emission of particles and rays. Now the particles are going to be the alpha particles and the beta particles, and the rays are going to be gamma radiation, where instead of rays we more commonly use the term photons. So hopefully you understand that. Now we just need to do a little bit of history. When was radioactivity discovered? Well, it wasn't discovered by this hot guy, Wilhelm Röntgen, but he discovered X-rays. And X-rays are energetic particles that come from the interactions of atoms, but not from the decay of atoms. But it was the starting ground. People started getting interesting on what happens in atoms and nucleuses and their interactions. That's what he looked like, in case you didn't know what he looked like. And what he did was he took X-rays. And this is an X-ray of his wife. That's the wedding ring and the bones in her hand. And most of us have had an X-ray, so we're pretty familiar with those. Oops, let's go back. We jumped ahead. Too many clicks. Now this guy, Henry Becquerel, he was looking at X-rays. So that's the follow-on from X-rays. And he was studying X-rays by looking at what they were doing to photographic paper. And in his lab he had lots of photographic paper, and he was holding the pieces of paper down on the desks and things, his benches. He had paperweights, and one of the paperweights was a thing called pitch blende. And what he noticed, being a scientist trained to observe, he noticed that when he used that paper that had been held down by the pitch blende paperweight, he would see an outline of the paperweight. Didn't happen with any of his other paperweights. And so he started to look at it, and he came to the conclusion that there was something within this paperweight, the rock called pitchblende, that was causing the photographic paper to change colour. And that was the starting of the discovery of radiation, or radioactivity, sorry, to be more precise, because Marie Sklodowska and her husband, Pierre Curie. Marie used to be called Marie Curie, but people tend to think that she didn't actually end up taking her husband's name. She was a physicist and he was a chemist, and they introduced the term radioactivity because they took this pitchblende, they took a ton of it and refined it down and processed it and worked out that it was all this clouding of photographic paper was all caused by a element that had previously never been discovered, radium. And they also discovered polonium, and they coined the term radioactivity. There they are in the lab together. Unfortunately, it's not always a happy ending. Pierre was killed by a horse, and Marie died from leukemia, most likely a result of her spending years working with radioactive materials. However, they got recognised in science and in physics and chemistry, because the highest award that you can get in physics and chemistry are Nobel Prizes, and Pierre was awarded one, and Marie was awarded two, which is not a common occurrence, and one in physics and one in chemistry. Now, we also need to just touch on, in our introduction to radioactivity, a thing called background radiation. Now, background radiation is and it really should be called background radioactivity, because we're talking about the ionizing radiation that's emitted by natural and artificial sources, and which we get every day. Basically, it's always here, and the human body has evolved, in fact all living life on Earth has evolved to cope with a certain degree of ionizing radiation. And so if we looked at the sources of this background radiation, we have the sources from the Earth. The food you eat is slightly radioactive, water, building materials, because everything on the Earth is a combination of all these elements which are radioactive. For example, most of the food you have is radioactive, but something like a banana is a little bit more radioactive because it has a little bit more potassium in it. Sources from space, in the form of cosmic rays coming from the sun and from outside of our solar system. We're moderately protected by the Earth's magnetic field. However, some gets through, and so we're always exposed to it. And sources from the atmosphere, which are mainly radon gas, which is released from the crust. And so we have Earth, space and atmosphere, and we're getting that radiation all the time, and we'll look at it in the classroom when we get our Geiger counters out. Now, the artificial sources, which include a whole range of things which you may or may not have been exposed to. Medical procedures. So have you had an x-ray for your teeth, for your bones? Do you have a smoke detector? Even though it's shielded, it's giving off a little bit of radioactivity. There are some signs that are radioactive, so that emergency signs that glow in the dark. Not all glow in the dark things are radioactive, but some are, and the way they glow is because they're doped with a little bit of radioactive material. There's global radioactive contamination, and that's a result of weapons testing. And on your OneNote there'll be a little video on all the weapon testing that has occurred since the discovery of the atomic bomb, and all that weapons testing has made the whole world a little bit more radioactive. You, me, everybody. There's also been some nuclear accidents, and the burning of fossil fuels is also increasing the background radiation, because we're releasing a lot of carbon, and that carbon is radioactive, and instead of being buried in the earth where the radioactivity wouldn't get out of the earth to affect us, we're burning it, putting it in the atmosphere, and therefore making ourselves a little bit more radioactive as a result. Now, your annual dose of radiation is approximately 82% natural and 18% man-made. Now, if you went back a couple of hundred years, this man-made ratio would be close to 0. And what's it made up of? Well, there you go. 12% for food, 10% for cosmic rays, 40% for gamma rays from the ground, 50% radioactive gases in the home, which are just seeping up out of the crust. Can't do anything about that really. 12% from medical, less than 1% from nuclear waste, occupational, depending on where you work, 0.4% from fallout from those radioactive tests. Air travel, if you do a lot of air travel, because you're flying high in the atmosphere, you get a lot more radiation, and people like flight attendants and commercial pilots, they actually get limited to how many long haul flights they can do in a certain period of time because of the increased radiation. It's only if you're a frequent flyer that it would be a problem for passengers. I think there's another one here. This is the Australian one, similar but different. Internal radiation, external cosmic, radon, medical. Now there's a little video as well called that is the one I was talking about in terms of nuclear testing, and that is on the OneNote in class. Now that's the end of that video. Next video will be on detecting radioactivity. Cheerio.